Section 12.10 addresses sound intensity. Now, in the previous section, we talked about the range of frequencies that the human ear could hear, something like 20 hertz to 20 kilohertz. So that had a really large range, but it's nothing compared to the range of sound intensities which the human ear can hear. So first, we're going to point out that we're going to have intensity, and we're going to use the symbol I, and this is going to be the average power and power given in watts, like we saw in an earlier physics class on mechanics. That's the average power transported per unit area. So writing that out, we know that power is in watts and a unit area would be meters squared. So the units would be a watt per meter squared. First, we'll talk about in order to get that power associated with a sound intensity being transmitted from a source, we're going to have the power of the source itself. So if we consider a few separate sources of sound, a person talking in a conversational tone, so I'll just write conversational tone, is going to be rather small. It's about 10 to the minus 5 watts. And somebody shouting is going to be, of course, greater, and that might be around 3 times 10 to the minus 2 watts. And so if you somehow magically had 10 to the 7 or 10 million people, imagine that I spelled people correctly, but 10 to the 7 people talking at once, you can imagine that might be, if they were in a small enough area, about 100 watts, which sounds pretty small. Another thing about sound intensity, it can be related to the amplitude of the sound wave, and that would be what we had spoken of before, a variation in the pressure and the intensity of sound. The power would be also proportional to the frequency squared. So we can say intensity of sound I, and I would write alpha for is proportional to the amplitude squared. So we talked about the amplitude in the case of sound being a pressure variation up to about 30 Pascal out of a base 1.0 times 10 to the 5 Pascal standard pressure at standard temperature and pressure. And then also that sound intensity is going to be proportional to that frequency squared. So if you double the frequency of a sound with the same amplitude, that doubling of frequency is going to lead to 4 times greater intensity in the sound. Now, if we have a sound source and we go a certain distance away from that source, I'll call this a source of sound, and I go a distance r away. If this source broadcasts in all directions, then this thing is going to have some power, and that power is going to radiate outwards in all directions. Imagine that I've drawn a perfect circle here. And the intensity of the sound on the surface of that circle, or if you're looking at it in 3 dimensions, on the surface of that sphere, is going to be equal to the power you put into the sound divided by the surface area of a sphere. So the surface area of a sphere of radius r is going to be, here I should have written surface area here, 4 pi r squared. So that intensity at a distance r away from the source generating a power P is going to be P over 4 pi r squared, like that. Now we're going to use this over and over. We're going to talk about it right now just for sound, but we're also going to talk about it when we talk about a light source. So a light bulb or a star. something that is generating power and putting it into some sort of radiation, be it sound radiation or light radiation, well, the intensity of that source at a distance r is going to be described by this equation here. In terms of units, remember this is the same thing that we just talked about for intensity, watts per unit area or watts per meter squared. And notice this, if I have a power source here and I go out a distance R1 and I draw my spherical surface, actually maybe I should draw the spherical surface and then my radius vector after, and then I go a distance out R2, and this central point is going to have a power generated of P. Notice that power generated is going to be related to the surface area of that sphere and the intensity on the surface of that sphere by this relation. Remember, I get this just because I had I equals P over 4 pi r squared. My point that I'm trying to make, or about to make here, is that the power is the same, regardless of how far away you are from that source. The farther away you get, the lower intensity you're going to hear. But notice that P is going to be equal to 4 pi, and if we go to that first spherical surface, 4 pi r1 squared times I1, the intensity that somebody would perceive at that radius, and that's going to be equal to 4 pi r2 squared times I2. And so here we get a relationship between the relative intensity at 1 and 2. So I1 divided by I2 can be found by algebraically manipulating this expression here, and we find that ratio of intensities is going to be related to the ratio of the radii squared, like that. Like I said, this holds true for light sources as well. The big example for this would be, if you're on the surface of Earth, you're going to see a certain intensity of sunlight because we're a certain distance from the sun. If we go to a planet that's farther away from the sun, like Mars, that radius is going to increase, and you're going to get a corresponding drop in the intensity of light that you see. And at each planet, you're going farther out. By the time you get out to Jupiter, for instance, I think it's maybe 4 times farther away from the sun than the Earth is. By the time you get out to Pluto, which isn't a planet anymore, but it's 40 times farther away. And so it's going to be 1 over, 40 squared of the intensity that you receive. Now, I pointed out before that there's a wide range of sound intensity that the human ear can hear. So if we talk about intensity, again, a whisper, if you are listening to somebody whisper, that level of intensity is going to be very small. At the lowest, at the lowest level or threshold of human hearing, that could be around 10 to the minus 12 watts per meter squared. And if you get up to the level of, a watt per meter squared, you're going to experience pain. So we're going to call this the threshold of pain. Although I may have misspelled threshold. Anyway, it's going to be around 1 watt per meter squared. So that is a huge range. It's, it's a factor of 10 to the 12 different in intensities. But we want to have a better way of describing sound, and the way sound intensity, so that the numbers we use aren't ridiculous. It would be tedious to say, well, this is 5.67 times 10 to the minus 6 watts per meter squared versus 0.56 watts per meter squared. In order to handle this huge range, we use a decibel scale. And this is going to be a logarithmic scale. Basically, we would just take that intensity in watts per meter squared, and we take a logarithm of it. And so when we describe these different sound intensities, it gives us a smaller range of numbers that are describing it. If we just jump right into it, we're going to say this. The sound level described in decibels is going to be denoted by beta. And we're going to say this. It's going to be equal to 10 decibels times the log, and this is going to be a log base 10 of the intensity here to some reference intensity. And it turns out for this reference intensity, we're going to use that lowest level, that threshold of human hearing of 10 to the minus 12 watts per meter squared, like that. So when we take these intensities that I talked about, we plug them through this operation, we're going to get something interesting out of it, which is this. For a whisper, it's going to be somewhere between 10 and 20 decibels is going to be the sound level. And remember, when I'm talking about decibels, when I talk about the decibel system, I mean sound level. And when I talk in terms of watts per meter squared as my unit, and actually here I would say, a dB is my unit. When I talk about watts per meter squared, I mean a sound intensity. It's a subtle distinction. You just need to always be aware of what you mean when you express a sound level or a sound intensity. All right, like I said, for a whisper, it's going to be around 10 to 20 decibels. Ordinary speech, if I spell it correctly, is going to occur at around, it's going to occur at around 65 decibels. And finally, a loud concert is going to be around 140 decibels, which is very, very loud. I think the threshold of pain is somewhere around 110 to 120 decibels. Now, having written this out, we're going to go two ways with this. We're going to say, I have some intensity and I want to convert it to decibels. And so I use that operation. Another thing can occur that you want to know the intensity of sound, given that somebody just told you a sound level. They said something was at 15 decibels or 80 decibels, and you want to know the watts per meter squared. Well, you just have to do an inverse operation on this. So notice, if I want I, and I'm going to go through in a little bit of detail here. If I is what you want, I would do this. I would change, from right and left-hand sides. I would write log of I over I sub naught is equal to that sound level in decibels divided by 10 decibels. If somebody tells you something is like 85 dB, notice that this is going to have a dB in the numerator and the denominator, and they're going to cancel out. Now, this is log base 10. The inverse operation of log base 10 is to take something take 10 to the power of a number. And so what I write is this, that 10 to the log of some number A is equal to A, in the same way that log of 10 to the B is equal to B. The reason I write that out is because I'm going to take each side of this expression, and I'm going to raise 10 to that power. So this is going to give me, like I said, I'm just going to go a ton of detail. I over I sub naught, that's just equal to I over I sub naught. And that's going to be equal 10 to the beta divided by 10 dB. My final expression, if I have left myself room, is this, that I is equal to I sub naught 10 to the beta over 10 dB. So this gets you from an expression in decibels, a beta in decibels, to an I. Remember, to an I in watts per meter squared. And remember, again, that I sub naught is this reference value, 10 to the minus 12 watts per meter squared, a low range or low estimate of the limit of human hearing. And I want to do a quick example, just for giggles. At 65 decibels, the intensity is going to be I sub naught times 10 to the 65 dB divided by 35. Sorry, I don't know why I wrote the 35 there, by 10 dB. I'm jumping ahead to some final answer that I saw. When I write this out this way, I like it because you immediately see that I'm canceling out those decibels, and I have 10 to the 6.5 basically. I would have written 10 to the minus 12 watts per meter squared for the I sub naught value, and then 10 to the 6.5. When I plug all this into my calculator, I see that 65 dB, again, this is going to be, well, that is going to be in the range of a conversation, a normal conversation or something you're listening to. And this is going to be around 3.16 times 10 to the minus 6 watts per meter squared. You're going to do several operations using this formula. So it's worth going through this example and going through the examples in your book to make sure that you're comfortable using log base 10 and finding, 10 to some power. Just make sure you're comfortable using your calculator for these calculations.